Uh, well, first of all, thanks to Ruching and Tom for the invite and the audience for showing interest in the talks. My name is Veer Bhatt. I'm an application scientist with Thermo Fisher Scientific. And in this session, we are going to be talking about electron tomography in life sciences, technology and applications. So when we talk about 3D reconstruction at a nanometer to angstrom scale, there are three techniques: single particle analysis, microcrystal electron diffraction, and tomography. Because Heather already touched base on, she already introduced all three of them. So I'll skip next couple of slides and go straight to the primary focus of today's talk, which is tomography. So here is the basic idea behind tomography. So on left, we see we can imagine that we have a real 3D object, and we just walk around it to see it from different views. So views are like projections. Opposite to that, if we only had the views, which are projections, we could also do the inverse, which is recreate the 3D volume from the reconstructions. So that's the key idea behind tomography. So now, of course, it comes in many different flavors, and there are some additional advanced extensions to it. Cryo-electron tomography is one of the extensions, and it can be used to obtain 3D reconstructions from vitrified samples. It can also be used in combination with correlative microscopy and correlative electron microscopy, where we can specify the target locations. And we can also extend, in many cases, the resolution by using subtomogram averaging workflows. Just to get a quick look on what kind of results do we expect from tomography. So here, from room temperature samples, we have heart muscle tissue from mouse. So we see the aligned tilt series on left, and the volumetric reconstruction coming from the same data on right. And there's a little bit of rendering as well in this image. And then here's an example from cryo-ET where the resolution was further extended from nanometer to angstrom scale by using subtomogram averaging. So here the sample is from Chlamydomonas, and it's a mitochondrial respirosome. So the group from Waltz et al., they were able to obtain a very high resolution reconstruction using cryo-electron tomography, followed by subtomogram averaging of all of these components. So just to kind of set the expectation for what kind of results do we get. Now, the question might be asked, why do we need to do tomography? Most importantly, the first point pretty much captures what's most important about this. And that is we are able to capture information in actual cellular or physiological context. Then there are some additional advantages as well. When compared with single particle analysis, we are capturing larger volumes. And also, with the exception of subtomogram averaging, we are not averaging our data, basically. So the key idea behind tomography, we acquire data, and we'll go through all these steps in more detail as we go through the talk. But after data acquisition, we perform an alignment, and that alignment is followed by reconstruction in 3D space. The reconstruction is then typically followed by segmentation to help us further and more clearly answer the scientific question we were seeking to answer. The workflow for tomography, a typical workflow would start with time alignments, setting up some filters and performing some calibrations, finding our region of interest, first at low magnification, and then we zoom in a little bit and capture the region of interest in high magnification. And finally, we configure and execute automated data acquisition. Now, in terms of alignment, I won't go through these in detail unless there are questions in QA session. But basically what we're trying to do is to make sure that the electron beam is aligned well with optical axis, in addition to many other things, but that's one of the primary things that we are seeking to do here. And that ensures that our images are the best possible that we can obtain with the system. Now, there are a couple of sources of non-eccentricity that we need to address because tomography heavily relies on you being able to tilt your stage while the sample stays in place somehow. And no system can be engineered or manufactured to be perfectly eccentric. So that's one intrinsic source of non-eccentricity. And in addition to that, there is also the offset between the tilt position. So this is where this is the axis looking down the screen where our sample will be tilted. And this is the point of intersection between optical axis of the electron beam. So there is a little bit of an offset, and we want this offset to be somehow minimized. And the way we do this is to calculate what we call optimized position. And what that does is that it calculates an image beam shift so that the tilt axis coincides as closely as possible with the optical axis. Okay. So that needs to be done only occasionally. But what we do need to address and perform frequently are the next few steps. So the next step here in this workflow would be to set up filters. And having the filters, first of all, what kind of filter am I talking about? I'm talking about a bandpass filter. So we don't want to look at too much detail of our image, but we just want to set up our spatial frequency according to the sample that we are working with. So having the filter set right is basically important for various auto functions, such as finding eccentric height, finding the right focus to work properly. And also, very importantly, it is crucial for tracking to work properly, and we'll discuss that further in a little bit. So here I set up the longest wavelength. Like I said, it's a bandpass filter, longest wavelength, shortest wavelength, and their slopes are set up. And then there are a few other parameters like setting up a Hanning window so that we don't see signal from the image edges, and setting up activating suppress zero peak so that the noise in one image is not matching the noise within the next image. So let's see this in action. Okay, so we set up these filters, acquire an image, we move the stage a little bit or tilt it a little bit and acquire a second image. And then we compare the images, the raw images, as well as the filtered images. So here we can see that the cross correlation between the raw images, the cross correlation peak is very diffuse as expected, but because of the filters set right, the cross correlation peak is very sharp for the filtered images, and that's exactly what we are looking for. If we are using similar types of samples, then of course we don't need to repeat this step very frequently as well. Okay. The next step would be go to the next slide. So the next step is image shift calibration. And this needs to be performed so that as our transmission electron microscope cycles through various magnifications, uh, it keeps our region of interest in the field of view. Okay, so let's see that in action in this example. So we start with the highest magnification. And then the software in the background is again calculating image beam shift that needs to be applied so that uh, the region of interest stays in the same place. That's the lowest magnification we'll be using. Okay, so our next step would be to find our region of interest. Now, to do that, we first acquire a really low magnification tiled data set. In this software, we call it Atlas. So we are driving the stage in a spiral fashion here. To capture basically the overview of the whole grid. So this is a slot grid and we see the heart muscle sample here. And towards the end, we can also adjust the threshold so that we enhance the features digitally and kind of figure out, again, the region of interest. Then this can be followed by another alum capture, a low magnification capture, but slightly higher in magnification. So we went from 115x to 700x. And we can adjust the threshold of the image here again to zoom in a little bit more on our region of interest. And finally, we go to the last image capture before we actually set up the data collection. So this step is in this software, it's called acquiring a search map. And a search map is basically a grid, just like we saw while capturing Atlas. So here we are going to capture a 3x3 tile set. We have a couple of additional options here, but not too many parameters. We can use image beam shift and we can change stage settling time a little bit. So here it's 5 seconds, and that's generally a little more than what we need. And when I start capturing it, this is how it looks like. Again, a sped up video of the capture. The key idea here is to drive us closer and more precise towards the region of interest. That's all what this exercise is really about. And once we are done with that, we acquire a search image where we will set up how the data acquisition is going to go. So the green region here is the area of acquisition, the square being the field of view for the detector, and the circle is the diameter of the beam, the electron beam. Now, let me make sure. Okay, I want to bring up another important point here, which is the blue line that you're seeing. That is the tilt axis, and you should note that we are adding additional areas away from the tilt axis. So this is something that has been recently introduced in tomography software, and this allows us to improve throughput of imaging drastically. So basically what we are doing here is we are going to add tilt angle, let's say 0 degrees, and we are acquiring an image here. And we are applying some beam shift and acquiring the next image here, and some beam shift again to acquire image in this area. So in this fashion, we are increasing throughput, because the alternative would be to acquire a tilt series here, wait for that to finish, go to this area, acquire a tilt series there, wait for that to finish, and then same with the next tilt series. So as long as our regions of interest are in close vicinity, we can employ off-axis data acquisition as well. So if we are talking throughput, then it increases throughput dramatically. And then, of course, once we are set up with this region of interest, we can go back to Atlas and overview images that we acquired earlier, find another region of interest, and we can queue that up here. So eventually, here in this example, I only have one line populated, but here we could have any number of like 20, 30, 40 sets of these kind of acquisitions queued up. Okay. Now, what are the different parameters that go into thinking and deciding how should I optimize my acquisition so that I get best possible reconstruction? First important parameter is, of course, magnification, because this is where you decide how with the features that you are looking for in your region of interest, how they are going to look visually. It also limits your resolution by Nyquist theorem. So we have to keep that in mind as well if you are thinking about going towards higher resolution. Tilt range, here finer tilts allow us to go towards higher resolution, but at some point we start losing time, and also the data becomes at some point too redundant. So we have to find a fine compromise between going between too fine of a tilt range and two big steps, which will then limit the resolution. Exposure, depending on what camera we have, in general, we want to stay close to the higher end of the dynamic range of that camera while keeping the dose rate compatible with the camera. So next is defocus. For many very heavily stained samples, we don't need to use a lot of defocus, but oftentimes, especially for dose sensitive and cryogenic samples, we do rely a lot on defocus because that's what brings in phase contrast, and we rely on phase contrast in turn to basically see what we want to see. Data acquisition scheme, I'll discuss a little bit in the next slide. And then there are holder predictions, which are pre-calculated trajectories for holders. They can, on occasion, they can save us some time, but wherever applicable, as long as you are using the same holder, they should not harm our acquisition. So it's advised to use them whenever they are available. Tracking strategy. Tracking is very important to keep our region of interest in the field of view. So we need to think about tracking, how we do tracking. Will generally, to make tracking work properly, we have to have sufficient defocus, sufficient exposure time, and many times we also like to go slightly lower in magnification so that tracking can work more efficiently, because it has more to see in the field of view than the exposure or the data acquisition magnification. Binning to improve contrast, but again, it comes at the cost of resolution. So we need to see what we are targeting. Are we targeting, for example, for room temperature data collection? Binning is generally carried out, but if we are thinking subtomogram averaging and really high resolutions, low angstrom scale, then binning is generally avoided for the final reconstructions. Might be done in the intermediate steps in the pipeline. Data acquisition scheme. So let's go to the next slide here. So a few options there. Continuous tilt scheme. For example, we do one continuous sweep with whatever 1, 2, or 3 degree increments, for example. With those sensitive like cryogenic samples, that means that by the time we are at 0 degree tilt, we are already our sample has already suffered a lot of radiation damage, and we have lost a lot of good signal which could have been captured. Similarly, the resin-embedded samples, they have already gone through a lot of additional deformation by the time we get to best possible images. Similar in nature is bidirectional scheme, but the only difference is that we kind of have two wedges of data. For example, from 0 degree to one segment could be from 0 degree to minus 60 degree, then another from 3 degrees to plus 60 degree. In contrast to these two, the approach that we like to use generally is, especially for cryogenic samples, is dose-symmetric tilt scheme, where the tilts go kind of simultaneously in both directions. So for example, we start with 0 degree tilt, then to -3, then to +3 and +6, then in groups of 2 on both sides. So -6, -9, and likewise on both sides. So this ensures that there's an even distribution of radiation damage on both sides, but even more importantly, it also ensures that images near our 0 and lower tilts are capturing very good signal to noise. Okay. So here's an example from again from tomography software. So we are setting up many different parameters here that I was talking about. So the tilt span here is from -58 degrees to +60 degrees. Here we use a tilt step of 3 degrees in the beginning, but as we use a switch angle, which means that once we approach 45-degree tilt, then we reduce the tilt angle to 2 degrees so that we capture those high tilts because they have more thickness, so we capture them more finely. Group size, like I said, generally and most common is 2, but we are allowed to use higher ones as well, depending on the scenario. Then once that is done, we have several options for tracking as well. Sorry, this was supposed to be a movie and it's not playing very well. So for tracking, we can track before and after acquisition, and that is generally preferred. Focus, again, we can perform focus for every single image that we are planning to acquire, or at high tilt, sometimes what we do is we perform focus every 2 images as well. Adjust exposure time, we can extend exposure time as we go towards higher tilts because the electrons have to pass through thicker slabs in that region. And then once that is done, we can, it's working, so here, we set up the tracking here. And once we have set up these parameters, we can start the data acquisition. Speed up video, I'm going to skip most of it, but just a quick preview of how it goes. Okay. So the tilt series is exported here. So a couple of things to note here. Most importantly, what we are seeing here is that the field of view, the region of interest, stays within the field of view. It means that tracking has succeeded. So we are seeing a little bit of jitter, but we are not losing more than perhaps a few percent in field of view, and that's what we want to go for. The second thing is that our signal, our features look similar on both sides of the tilt, negative and positive. And what that means is the optimized position is calculated properly, and B, the focus is happening where it ought to happen, which is near the center of the field of view. Quick overview over the reconstruction workflow as well. So typically, the softwares start with XY or stack alignment using cross correlation, going from one image to the next, and so on, where we do use quite a bit of filters, just like we used earlier while tracking. This can already optimized tilt axis to a certain extent, but further adjustments can be also done in a separate step. So this overall alignment, the initial step, can sometimes be further improved by patch tracking or if we have fiducials. And once the alignment is complete, the next step is reconstruction using one of the available algorithms such as SERT, EM, or weighted back projections, and so on and so forth. So here is the reconstruction result from the tilt series we just acquired. And to kind of round up, we do have, there are softwares that can automate the process. TomoLive is one example of such a software which can basically give live feedback and perform these reconstructions in a very automated fashion. So here, for example, we have a cryogenic data set which is subjected live. So as the data are being acquired, they are motion corrected and aligned, and CTF is estimated. And as soon as the data acquisition is complete, the reconstruction happens within the next few minutes. So there are some examples of this is how it goes live, how it works in a live fashion. Yeah. Okay, I think I'm already close to the end of my assigned time. So I think I'd end my talk here and take any questions that you might have.